We're diving into the fascinating world of systems of nonlinear equations. I'm Pearl, and together with my teammates, we'll guide you through what these equations are, how to solve them, and why they matter in real life. So what exactly are systems of nonlinear equations? Systems of nonlinear equation is a collection of two or more equations where at least one equation is not linear. Think of it as anything more complex than a straight line. So these are the examples of nonlinear equations. For example, y equals x raised to 3. So this is an example of nonlinear equations because x is raised to the power of 3. And so is 1 over x, xy equals 10, y equals c of x. Our goal is to find the set of values that satisfy all equations simultaneously. It's like finding the perfect meeting point for these equations. In solving systems of nonlinear equations, there are two methods. These are the algebraic method and the graphical method.
We'll solve the following system of equation using both algebraic and graphical method. First, the algebraic method. These involve manipulating the equations to find our solution. The most common technique here is substitution. These are the equations. Equation 1, x squared plus y equals 3. Equation 2, 3y equals 6. These are the step-by-step substitution method. Step 1. Solve one of the equations for one variable in terms of the other variable. 3y equals 6. We divide both sides into 3 and the answer is y equals 6 over 3. Then simplify 6 over 3 into y equals 2. Step 2. Substitute the resulting expressions in step 1 into other equation to obtain an equation in one variable. Solve the equation. X squared plus y equals 3. We substitute y into 2. And x squared equals 3 minus 2. Transpose positive 2 into negative 2. X squared equals 1. Then we should square it x squared and 1. X equals positive negative square root 1. X equals positive negative 1. Step 3. Substitute the value obtained in step 2 into the equation obtained in step 1 to solve for the value of other variable. Since we already have y equals 2, we don't need to substitute further. Step 4. Check if the solution satisfies the original equation. For x equals 1 and y equals 2. Equation 1, x squared plus y equals 3. We substitute x into 1. 1 squared plus 2 equals 3. 1 plus 2 equals 3. 3 equals 3. Therefore, our solution is correct. Equation 2, 3y equals 6. 3 times 2 because y is our 2 and the answer is 6. 6 equals 6. Therefore, our solution is correct. For x equals negative 1 and y equals 2. Equation 1, x squared plus y equals 3. We substitute x into negative 1. Negative 1 squared plus 2 equals 3. 1 plus 2 equals 3 and 3 equals 3. Therefore, our solution is correct. Equation 2, 3y equals 6. Our y is 2 and 3 times 2 equals 6. 6 equals 6. Therefore, our solution is correct. Therefore, the solution to the system of equations are 1, 2, and negative 1 and 2.
Now, let's visualize these with the graphical method. We'll use Dismos, a free online graphic tool, to plot our equations. First step, rewrite the equations. Solve each equation for y to make them easier to graph. First equation is y equals negative x squared plus c. Equation number 2 is y equals 6 over 3 or 2. Step number 2. Open Dismos. Step number 3. Enter the equations. In the Desmos, input boxes, enter the following equations. Y equals negative x squared plus 3, y equals 2. Step number 4. Identify the intersection points. This most will plot the two equations. Look for the points where the graphs intersects. The intersection points represent the solutions to the systems of equations. Step number 5. Read the solutions. Hover over each intersection point to see its coordinates. The intersection points are quantity -1 and 2 and quantity 1 and 2. From the graph, we can see the solutions are x equals to -1 and y equals 2. And the other one is x equals 1, y equals 2.
So where do these equations come into play in the real world? Let's talk about the air traffic control. Nonlinear equations are used to model the intersection of paths ensuring the safety of air travel. Imagine two aircrafts on different trajectories. Their paths can be described by nonlinear equations such as x squared plus y squared equals r squared for a circular path and y equals ax squared plus bx plus c for a parabolic path. Air traffic controllers use this equation to predict potential collision. By solving nonlinear equations, these can determine the points where the paths intersect. For example, if one aircraft is following a path described by x squared plus y squared equals 25 and another by y equals 0.5 squared minus 4. Solving this system will tell controllers if and where the paths cross. This allows them to take proactive measures like adjusting flight paths to prevent mid-air collision. It's critical application that keeps our skies safe.
And we highlighted a real-world application in an air traffic control where these equations play a vital role in ensuring safety.
To wrap things up, we've seen that solving systems of nonlinear equations can be solved using both algebraic and graphical methods.
We demonstrated this with a specific example, showing you step by step how to find the solution.
Nonlinear equations are more prevalent than one might think. They are essential for solving complex problems in various fields. They're not just abstract math, they have real-world consequences. Thank you for watching our video presentation. We hope you found it more engaging and informative.